Hello and welcome to the second part of our 4.1 section. We're going to continue to try to get comfortable with using radians today, and we're going to be looking at where in our quadrant system our different angles would lie and get used to looking at some of the more common radian measures. We're also going to be doing a little review of how to draw an angle in standard position in degrees, and then using that to do so in radians. So first we see this circle here that has a bunch of lines. Okay? We're going to consider each of these different lines a different angle measure, and these lines are called terminal arms. Okay? We're going to label all these lines in degrees and radians. Okay. Hopefully we already are comfortable with degrees because we should have done that in Math 11. But if not, this is going to be maybe a little bit more work for you. So first, we know that all of our axes measures here, the first one we can consider 0 degrees. Then the next one would be 90 degrees. Then we would have 180 degrees. And the bottom, we would have 270 degrees. And then we get back to our starting position, which means we've completed a whole circle at 360 degrees. Now, if I think about this in terms of radians, when I start, 0 degrees is also 0 radians. Okay. Now, I'm not going to keep writing radians every time. All my purple stuff will be on my radians. And a recollection from the previous lesson that if you see that little circle, that measure is in degrees. If there is no unit and you know it's an angle, then we assume that is radians. Okay. We knew that 180 degrees was pi radians. Halfway between those would be my 90 degrees, which is pi over 2 radians. Half of pi was pi over 2. Now, 270 degrees at the bottom would be halfway between pi and my full circle. My full circle would be 2 pi radians. 360 degrees was 2 pi radians. So halfway between 1 pi and 2 pi would be 1.5 pi. Now, we wouldn't usually write 1.5 pi. When we're dealing with radians, most of the time you're going to see them in fraction form. So instead of writing 1.5 pi, we're going to write 3 over 2 pi or 3 pi over 2. Now, if I go around the circle and I look at all of my solid lines that are sort of that faint blue or teal color there, yours, if you've printed out notes, will be black and white. So all of these ones here. Okay. In our first quadrant, we know that this first quadrant is everything from 0 to 90 degrees. Those lines have split that quadrant into 3 pieces. So that means the first one would be 30 degrees because that's a third of my 90. The next one would be 60 degrees because that's 2/3 of my 90. All right, now if I think of 1/3 of my 90 degrees here, I have 30 and 60 degrees. If I do 1/3 of pi over 2, what is a third pi over 2? Well, that should be pi over 6. Now, if I double 30 degrees, I get 60 degrees. If I double pi over 6, I would get 2 pi over 6, which is the same as pi over 3. Okay. So this already gives us some of our special angles. We know from Math 11 our special angles were 30, 60, 90, and 45 degrees. So I'm going to write these ones down. 30 degrees is equal to pi over 6 radians. 60 degrees is equal to pi over 3 radians. 90 degrees was pi over 2 radians. Now we just need 45 degrees. That was our other special angle from Math 11. So if I look at my first quadrant here, I also have this dashed line. This dashed line looks like it's cutting that quadrant in half. If I cut 90 degrees in half, I would get 45 degrees. And my corresponding radians, if I cut pi over 2 in half, I would get pi over 4. So that gives us our last special angle here. So these are our special angles. You know these, you can figure out pretty much all the other angles that are in this circle. And we're going to use that here in just a moment. As long as you know these four, you're pretty much set. Okay. So these ones you should make sure you know. Okay, these are important. Now we're going to use these to come up with all of our other angles in this circle. So all of the dashed lines are iterations of 45. So our quadrant 1 dashed line is 45. We double that, we get 90. Halfway between 90 and 180 would be another 45 degrees. So if I add 45 degrees to 90 degrees, I would get 135 degrees here. If I add another 45, I get 180. Add another 45, I get 225. Add another 45, I get that 270 we already wrote down. Add another 45, I get 315. Add another 45, I get 360. So kind of bopping between the solid block axis lines and the dashed lines, we're adding 45 degrees to get to each one. Now, if 45 degrees is pi over 4 radians, for our radian measures, we would add pi over 4 each time. So our first iteration was 45 degrees, or pi over 4. If I add another pi over 4, I would have 2 pi over 4, which gives me that pi over 2 at the top. If I add another pi over 4 to that, this is the same as 2 pi over 4. So if I add another pi over 4, I would get 3 pi over 4. Add another pi over 4. This would be 4 pi over 4. Add another pi over 4. 5 pi over 4. Add another pi over 4. 6 pi over 4. Then I'd have 7 pi over 4. And then I'd have 8 pi over 4. So all of our axes lines are simplified versions of my pi over 4. All of my dashed lines would be unsimplified versions of pi over 4 because we can't. Okay. We can do something similar with all of our iterations of 30 degrees. So 30 degrees was pi over 6. 60 degrees was 2 pi over 6, which happened to simplify to pi over 3. Then my 90 degrees would be 3 pi over 6, which simplified to pi over 2. The next one would be 4 pi over 6, which could simplify to 2 pi over 3. Then I would have 5 pi over 6. Then I would have 6 pi over 6. Then I would have 7 pi over 6. Then I would have 8 pi over 6, which I can simplify. Then I would have the next one would be 9 pi over 6, which simplifies to 3 pi over 2. Then I would have 10 pi over 6, which simplifies to be 5 pi over 3. Then 11 pi over 6. And then 12 pi over 6, which simplifies to 2 pi. So using my 30 degrees, I can go on all of those kind of blue, tealy solid lines. Now, if I looked at just the 60 degrees, I'd be looking at every other solid line. So my 60 degrees, if I double that, I get 120 degrees, which would be from pi over 3. If I double that, I get 2 pi over 3, which I've already labeled. Then I would have 3 pi over 3, which is my pi. Then I'd have 4 pi over 3, which I already labeled down here. Then I would have 5 pi over 3. Then I would have 6 pi over 3, which is equal to 2 pi. So we can see that all of my 60 degrees iterations are already covered when we did the 30 degrees. Now we can also go and add in the degrees measures for all these. We get 30, 60, 90. The next one would be 120, 150, 180, 210, 240, 270, 300, 330, 360. So hopefully this will help you as you start to try labeling where different angles will go. And when you're starting your questions, these might be useful to have out possibly even, but you would not have this on something like a test. Okay, but if you know those ones in that bubble on the side, that black bubble, then you should be okay to replicate all the rest of them. So just when you are going through questions, your angles will be measured something like this. The angle on the bottom x-axis should always go in that exact spot. That's called your initial arm. It always goes on the positive x-axis. The other arm is your terminal arm. And that's the one that will move around the circle as you change your angle theta. Okay. So let P be a point on the circle, right? Anywhere along the circle. If we measure an angle counterclockwise, which is how we just went around the circle, we went starting from that positive x-axis, we moved around counterclockwise. Then we have our terminal arm, and wherever our terminal arm ends, that point on the terminal arm that crosses your circle would be point P, and we call this an angle in standard position. If we measure our angle in the other direction, meaning that when we start going this direction instead, that would be a negative angle. Okay. So hopefully in grade 11, you covered standard angles in standard position from the positive direction, meaning counterclockwise, using degrees. The extension this year is now we're going to look at radians, and we will also look at negative angles. So for example, if I want to draw the angle 30 degrees, hopefully we know that that is in quadrant 1. Okay, so remember this is called quadrant 1. This one's quadrant 2, quadrant 3, and quadrant 4. So 30 degrees should be in quadrant 1, and this would be measured right here. 390 degrees, we start in the same spot. We would have to complete an entire circle, which is 360, and then an additional 30 degrees, which means we're actually going to end up in the same spot as our 30 degrees. So our terminal arms are in the same location. The difference is the 30 degrees you've just traveled a little bit. The 390 degrees, you had to do a whole circle plus an extra 30. Okay. So the difference here is that we have a little bit farther to travel, but our terminal arms are in the same spot. Okay. For the next one, we're going to try 3 pi over 4. So if you're not comfortable with radians yet, it's probably helpful to write 0, pi, pi over 2, and 3 pi over 2 on your axis lines until you get comfortable with where the radians go. 3 pi over 4 is like saying 75% of a pi, right? You didn't even travel to pi, but you traveled more than halfway. So 3 pi over 4 was in quadrant 2, which you can tell by the circle at the top of the page. And we would have traveled in the positive direction, which is counterclockwise. Now, the next one's a little bit more difficult. If we traveled negative 5 pi over 4, this means we're traveling the opposite direction. We're going clockwise. So we're starting at that positive x-axis, and instead of traveling up and to the left, traveling down and to the left. Pi would be 4 pi over 4, but I traveled 5 pi over 4 in this direction. So I traveled a little bit further, and again, I ended up in the same terminal position as my first angle. That additional pi over 4 that I have to travel. Okay, I didn't travel 3/4 of the way around my whole circle. I traveled halfway around my whole circle, which is pi radians, and a little bit further. Now, these angles that we just drew have a special name. Okay, they end at the same terminal arm. They are called coterminal. Okay, that's on the next page here. So we could go around a circle 1,000 times before we stop at our terminal arm. We could go around 10 times. We could go in a negative direction. We stop at the same terminal arm. We are considered coterminal. So there are an infinite number of angles which are coterminal with each other, depending on how many times around the circle you've gone, if you've gone in a positive direction or a negative direction. These can be found by adding or subtracting multiples of 360. So if I subtract 360, that would be like going around the circle one less time. If I add 360, that would be like going around one more time. If I add 360 10 times, that's like going around the circle 10 more times. Okay? We would also use 2 pi if we were talking about an angle in radians. So you need to be careful. If I have a radian angle, I shouldn't be adding or subtracting 360. I should be adding or subtracting 2 pi. So in degrees, we would take our angle and I would add 360 degrees times n. N is the number of times we're going to go around the circle. N needs to be an integer. So we write n is a subset of integers. Now, the book will use I for integers. Problem is that this is not a common use in the broader mathematical community for integers. So you may be using a Z with 2 lines instead. So you're probably used to writing something like this, but with an R with 2 lines for all real numbers when you're talking about things like domain and range. For us, we're using this to represent integers. Okay. So how we read this is theta plus 360n, where n is in the set of all integers. Okay, so we can't have any decimals. If we had decimals, we haven't traveled a full circle. Okay. In radians, we would use our theta, but we would be adding 2 pi n, because 2 pi is our entire circle in radians, and we would do that n times. And we can write n is in the set of all integers, or n is in the set of all integers using this double-sided z here. Okay, I will be using the double-sided z most of the time. So we're going to try a couple questions here. If I'm going too fast, feel free to pause so that you can catch up, write down, scroll back if you need to. So we're going to graph each angle below and then write a general equation to express its coterminal angle. So my 210 degrees, hopefully we know that that is in quadrant 3, traveled more than a half circle, but not quite 3/4 of a circle. My coterminal angles we're going to write like how we have above here. Okay, so my coterminal angles would be 210 plus 360n, where n is an integer. That's it. That's a general equation. Okay, we might add a theta equals in the front. Negative pi over 6, this means we are going clockwise. Remember, pi over 6 was 30 degrees, so we're not traveling very far. So we're traveling in this direction clockwise. We're not even making it to our next axis line. Okay, that's it, 30 degrees in the negative direction. And our general equation would be negative pi over 6 plus, we would write 2 pi n because our angle is not in degrees, it's in radians. And n is an integer. All right, let's try one last question here. So it's saying given theta is pi over 2. So remember, pi over 2 is this axis line here, 90 degrees. Okay. It wants to find all angles that are coterminal in this domain here. Okay. It's not a general equation. So coterminal means I'm adding or subtracting 2 pi, entire circles. So if I take pi over 2 and I add an entire circle, that should give me pi over 2 plus 4 pi over 2, which is 5 pi over 2. Now, you might look and go, well, how do I know if that's in the domain? Since these are all pi over 2s and we're going to just keep adding entire circles, our answers are going to continue to be over 2. So what I would do if I were you is I would change my domain to be negative 4 pi over 2 to 8 pi over 2. So I would make a common denominator with my domain so that it's easy to compare. So now the question is, does 5 pi over 2 fit into this domain? Well, it's bigger than negative and it's smaller than 8 pi over 2. So yes, I'm going to include this one. Now, if I add another circle to this, I would have 5 pi over 2 plus 2 pi, which is 5 pi over 2 plus 4 pi over 2, which would give me 9 pi over 2. This does not work because 9 pi over 2 is not smaller than 8 pi over 2. It's too big. So there's no point in me continuing to add 2 pi because I already found one that's too big. So I took my original pi over 2 and added a full circle and got 5 pi over 2. That one was okay. Then I added another full circle and I got an answer that was too big. No good. I can also subtract full circles. So if I take my original angle and I start subtracting circles, so if I subtract 2 pi, that would be like subtracting 4 pi over 2, which would give me negative 3 pi over 2. This works because I'm allowed to go all the way down to 4 pi over 2. So this one's okay. Now, you can probably tell already that if I try and subtract another circle, it's not going to work. But if you can't tell that and you're like, well, I guess I got to keep going. Now, if I subtract another circle from this, I get negative 3 pi over 2 minus 4 pi over 2, which is negative 7 pi over 2. And that doesn't work. I'm only allowed to go down to 4 pi over 2 here, negative 4 pi over 2. So this is too small. Okay. So my only coterminal angles in this domain are 5 pi over 2 and negative 3 pi over 2. So all your coterminal angles are is if you keep adding entire circles or subtracting entire circles. If you're given a domain, then you have to stop when your answers get too big or too small. So that's it for this section. This is something where you will need a lot of practice. It takes a lot of practice to get comfortable with your radians. That's why I've gone slow in this video. So hopefully you were able to follow along.